All right. This is for Physics 212. This is lab number 3. I'm going to attempt to explain Gauss's law using an example from the textbook, which is that of a sphere. So I guess for some context, let's think about a sphere. It goes around, it's three-dimensional, and in this case of Gauss's law, for this example, you have a charge that's right in the center of the sphere, and it's going outward. As electric charges go outward, they essentially make vector arrows going in all three dimensions. So one thing to keep in mind is that the area for a sphere is 4 pi r squared, I believe. And the surface area is 4 thirds pi r to the third. Um, Charging close. Sorry, I'm just reading this as we're doing this. And so you have to kind of think about um, how you're going to measure the charge, whether it's on the inside of the sphere. Like, let's say the radius is 10 centimeters, and there's a charge that's in a circle around the sphere that is about, I don't know, let's say 2 centimeters. There's going to be two different equations based off of that. Um, and I think the reason for that, this is where I'm probably getting a little bit lost in the weeds, um, is that you're going to measure the sphere a little bit differently on the outside as opposed to the inside, because on the outside there isn't. I'm not sure exactly why. Actually, that's a good question. I wish I knew why. I probably should know that. Hold on, let me look at my notes as I try and teach this. Um, oh goodness, that was from Wednesday. I'm trying to figure out why you use two different equations. Um, so if it's hollow, then the electric field um, is zero, and it has to do with the symmetry. Let me read this over a second. Oh yeah, because it's on the outside. You're gonna do the radius squared. Um, like if there's like a circle on the outside, you got the sphere here, and then there's you're measuring the electrical charge going out from the sphere around the outside of the sphere, um, and that's just going to be the charge or kq over r squared. Um, because remember the area was 4 pi r squared, and so you kind of derive it from that. But on the inside, it's it's qr, so it's the radius for this is for a solid sphere, over 4 pi e a to the third. So I think because it's a is the radius of the sphere, so in this case it was 10, is going to be to the third power, and the 4 pi, then you're going to do, yeah, whatever the actual measurement, so the 2 centimeters on the top divided by um, the entire sphere around that. That makes sense. Yeah, so I guess the best way to think about this is like you got rings inside and on the outside, and then you have the sphere, and you're measuring it differently of the electrical charges going out in three dimensions from the center of the sphere. Um, that then you're trying to figure out what the electrical charge would be at different distances. And so in this case, um, oh yeah, okay. Notice that E out has the same form as the equation of the electric field of an isolated point charge. In determining the electric field of a uniform spherical charge distribution, we can therefore assume that all of the charge inside the appropriate spherical Gaussian surface is located at the center of the distribution. Since, yeah, it's saying it's going in, okay, yeah, in equal directions. Okay, this graph, I wish I could show on the screen. Um, I guess I could kind of draw it out. Um, Varying magnitude electric distance from the center. Just for reference, I'm doing example 6.6, or at least trying to. um, the ratio of the electric field to the radius is proportional inside the charge distribution, but then once you get outside, the electrical charge is proportional to 1 over the radius squared. And I assume that would be because as you get farther away, you lose more of the electrical charge. But like it increases until you from the center to all the way to 10 centimeters at the sphere, and then it decreases once you get outside. And so that's that chart going like that, if I'm understanding that correctly. And then you can kind of measure it be R. On the inside it'd be R over 2, then it'd be R, and then it'd be 2R. No, wait, that's not right. Oh, interesting. Specifically, the charge enclosed grows proportional to R to the third, whereas the field from each infinitesimal element of a charge drops off a proportion of 1 over R squared. The result is that the electric field within the distribution increases in strength linearly with the radius. The magnitude of the electric field outside the sphere decreases as you go away from the charge. There you go. Because the included charge remains the same, but the distance increases. So yeah, you get farther and farther away. And I think that kind of relates to the same thing as gravity. And there's like zero gravity as you get to the center of the Earth, and then the gravity increases again as you get to the outside. That's another like more conceptual way to think about this. Let me look that over before I go spewing off. Oh yeah, here we go. And this is in the context of a solid sphere. Yeah, you have low to no gravity as you are in the center of the Earth, but then as you get away, then you have more gravity again. It's pretty crazy. Oh no, you have no gravity at the center of the Earth, and then yeah, as you get to this, the surface of the Earth, you have the most gravity, and then as you go out into outer space, you have no gravity. There we go. Okay, I think I got this down. I've explained pretty much everything about electric fields in regards to the sphere and how you have to conceptualize that with the radius when you're thinking about the inside compared to the surface, compared to outside, as the electric vectors within the electric field go in all different directions. Because remember, this is three-dimensional, and so you have to be thinking in those terms. And there's certain equations that I went over that equate to those different scenarios. And so obviously there's a difference between hollow and solid. I went more into the solid just because I felt like that was a good example. And yeah,